The first evidence for evolution is fossils, right? So basically, we believe that evolution is true because we can string together different fossils from different eras, and we can see the gradual change in the species. So, for example, the recent horse is in the Equus family. If you go back to the fossil evidence, you can see a fossil there from the late Miocene period of a organism called Phliohippus. And this Phliohippus fossil actually has similar characteristics to that of our recent Equus, the modern horse, but there are slight differences. And then, as you go back further in time, you can find another fossil from the Merychippus during the middle Miocene period. And in this fossil, again, has differences from the Phliohippus, but a little bit. So you see the changes are becoming greater and greater as you go back further into the fossil period, fossil time. And then after that, you can even find a fossil during the late Eocene period, which is now earlier than the middle Miocene period, and you can see a Mesohippus fossil, and that fossil is quite similar to our modern horse, but quite different. And if you string together the fossils, you can actually see the gradual change in the bone structure, in the anatomical structure, and that's why we believe that this is how evolution works. Evolution actually shapes the species to become another species gradually, feature by feature, bone by bone, until they become a different species. However, there is a question, and I know you have been asking this also in your mind, and that is, how do we know the age of the fossils? Right? Because in our argument, we can string together fossils according to the time period, and we can see the gradual change in the skeleton. But how do scientists determine the age of the fossils? I mean, they could just be making that up, right? Well, no, because there are techniques, and one of the techniques, and there are two techniques actually for dating the age of the fossil. One is called absolute dating, and the other is relative dating. So, absolute dating is when you can really find out the age of the fossil from the fossil itself. So you see, most fossils are bones, but there are some fossils that include some tissues in it. And if it includes some tissues, since we are carbon-based, remember, then some of the carbon in that tissue material is carbon 14 or carbon 12. Now, carbon 14 is actually radioactive. That means that it's not stable. So, carbon 14 actually decays into nitrogen 14. However, the thing is, carbon 14 decays into nitrogen 14 predictably at a specific rate. And that rate is called the half-life. And the half-life of carbon 14 is actually 5,730 years per half-life. What that means is if you have 100 carbon 14s, after 5,730 years, that number would go down to 50. Only 50 will remain. The other 50, the half, would have decayed into nitrogen 14. And then give it another 5,730 years, half of the 50 would decay into nitrogen and only 25 would be left. So that's why it's called half-life, because it's not like a constant rate. It doesn't decay like 10 atoms per year or something. It's kind of logarithmic because you take half of the half of the half of the half. So if you start with 200 atoms, after half-life, you left with half of 200, which is 100. After another half-life, half of what is left would decay, and again after another half-life, it's another half. So the rate there is the number of years, but the number of atoms that decay is always half of whatever was left in the first place. So that's why we call this half-life. Now, say for example you get a fossil, and that fossil has some carbon tissue in it, and the carbon tissue, scientists can actually examine how much carbon 14 is left, right? So if for example they're expecting 20 carbon 14 atoms to still be there. You see, not all carbon atoms are carbon 14. Most of them are carbon 12, but some are carbon 14. Now, if the scientists expect that in this piece of tissue there should be 20 carbon 14 atoms, but then what they found out was there are only 10 carbon atoms. What does that mean? That means it has already been one half-life since the organism died. Okay? So what that means is if they're expecting 20 but they only found 10, that means half was left. That means one half-life has passed. That means the organism was living 5,730 years ago, because that's one half-life. That's the length of one half-life of carbon 14. Now, you might be thinking, but how would they know the original number of carbon 14? Well, that's the magic of life, because you see, as long as living organisms are alive, they intake a certain isotope of nitrogen and carbon in the air, because they're still living. And so even if their carbon 14 are disintegrating, they keep replenishing the carbon 14 in their bodies as long as they're still alive. But the moment they die, they don't breathe anymore, so the carbon 14 reserves in their bodies would decline. So therefore, you would know a specific ratio that is supposed to be the correct ratio if the living thing is still alive. Okay, so again, you get a piece of tissue. Scientists expect that for this area you should find 200,000 atoms, but then you only find 100,000 atoms. That means one half-life must have passed. So that's why we can date bones of dinosaurs up to how many million years ago they were living. We estimate they have been living around 60 million years ago. That's for the dinosaurs. But for the other fossils, that's how we are able to date them. So that's what we call absolute dating, right? Absolute dating. Now, the second method is called relative dating, right? So I'm gonna relative dating. It's not when you date your relative or your cousin. Yeah, I just had to say it because it's in my head. But anyways, relative dating means that you find out the date of the fossil not based on some high-tech technique like the absolute dating technique, which is radioisotope dating, but you infer it from the layer of rock from which the fossil was found in. So for example, you have a sedimentary deposits, and then you find a fossil there. What you do is you mark in what layer you found that fossil in. You take a photograph, and then, because geologists have this databases of their data that they have been collecting about the ages of these rocks. So what you can find is there might be a layer somewhere along the same formation that formed the sedimentary rock that has already been dated, right? And what you do is you compare the layers, because you see the layers of sedimentary rock, sometimes There are thick sediments, sometimes there are thin sediments, sometimes they're thick, and it depends on the year, and so it becomes a fingerprint. So there is no segment of sedimentary rock from different layers that are the same. It's always like a fingerprint. So if you find that, for example, in the third line in this structure, and then you take a photograph of those lines, and then you compare it to another layer that has already been dated, right? It has already been dated, and you find out that this layer, the third line where your fossil was buried in, is aged 30 million years ago, then that means your animal must have lived 30 million years ago. Otherwise, why would he be stuck in between the layers, right? It's not like, I mean, see, the sedimentation process is quite, I mean, you can make a sedimentary rock and then insert something inside. If something is inserted in the layer, that means it must have died when that layer was being formed. Okay? So if you find a fossil in the layer that has been dated 15 million years, that means your organism must have lived at that time period. It's not possible. You don't have a case where the layer was formed and then somehow you insert the organism there. That's just not possible. Okay? So that's what we call relative dating. So we know the age of the fossils because of these two techniques. Okay? like for example, plate tectonics. Remember plate tectonics? First grading period. We know that the rock layers in South America and Africa are the same, right? And they actually just diverged, right? So for example, you have rock layers here, and then you find, for example, a fossil in a particular layer, right? But you don't know the age of the layers. That's no problem, because remember, the same layer was formed and then they broke into two continents. So maybe a geologist somewhere in South America was able to find a technique, was able to find another way to find out the age of the layers, right? So all you have to do now is go to the database and try to find in which particular layer your fossil was buried in, and you can cross-reference it to the data taken from the other side of the continent, and voila, you have the date. Okay? So two methods of dating fossils. Absolute dating, which uses radioactive isotopes, like for example, carbon, right? Even rocks, you can date rocks because rocks can also have uranium, and uranium is also radioactive. So you can date them through carbon dating or through uranium dating. That's what we call radioactive dating in general. So that's absolute dating. You really find out the age of the particular rock. And then you have relative dating, wherein you try to make an inference of the age of your fossil based on the layer in which it was buried in. So two methods of dating, absolute and relative.